In section 6.4, we'll define enthalpy and learn how to calculate pressure volume work. Specifically, we'll connect the concept of internal energy to enthalpy, discuss the relationship between pressure, volume. Then we'll learn the terms and signs used to describe the flow of heat associated with enthalpy. Let's begin. We saw previously that the formation of a gas from a chemical reaction can be used to push a piston in the system. We can calculate the amount of work done by multiplying the pressure in the system by the volume change. Delta V here means we'll take the final volume and subtract the initial volume from it, and we wind up with these weird units of liter atmospheres from the product, which we can convert to joules using the relationship that 1 liter atmosphere is equal to 101.325 joules. Finally, since pressure volume work is done by the system on the surroundings, we indicate the flow of energy out of the system with a negative sign. Let's look at an example. Calculate the amount of work performed in joules during this reaction when the volume decreases from 0.550 liters to 0.375 liters. First, calculate delta V. Then, calculate W. Finally, convert to joules. Determine whether the piston moves upward or downward over the course of this reaction. The sign of W is positive, so the surroundings do work on the system. This is supported by the negative sign of delta V, which tells you that the piston moves downward. Most chemical reactions are performed in open systems, with exchange of both heat and work between system and surroundings, because chemists are most often interested in the flow of heat in systems at constant atmospheric pressure. Enthalpy is a state function that relates internal energy, pressure, and volume. Keeping in mind that the absolute values of internal energy are hard to quantify, we'll move from this definition to describing the changes in enthalpy as the change in internal energy plus any pressure volume work that occurs, so delta H equals delta U plus P delta V. We can substitute Q plus W for delta U, which gives us delta H is Q at constant pressure plus W plus P delta V. We know work is also equal to negative P delta V, so plugging that in for positive P delta V gives us negative W. Simplifying, we see that delta H, the enthalpy change, is equal to the flow of heat at constant pressure. Following the same sign conventions as Q, we'll see that negative delta H indicates heat leaving the system to enter the surroundings, which we call an exothermic process. Think of the prefix exo as meaning outside the system. Positive delta H, just like positive Q, indicates heat entering the system from the surroundings. This is called an endothermic process. When wood is burned in an open fireplace, 250 kilojoules of heat is released, and the expansion of hot gases from the fire does 15 kilojoules of work on the surroundings. Is this reaction endo or exothermic? Heat is transferred from the system to the surroundings, so the reaction is exothermic, and delta H is less than 0. Calculate delta H for the reaction. Since this is an open system, the pressure is constant, and we can use delta H equals Q equals negative 250 kilojoules. Calculate delta U for this reaction. Use delta U equals Q plus W equals negative 250 kilojoules plus negative 15 kilojoules equals negative 265 kilojoules. As always, I'll leave you with the parting thoughts of the authors. Don't forget to let the video finish playing through so that your score transfers to Canvas.